So, hello everyone, welcome to the European Non-Associative Algebra Seminar. I'm glad to introduce the speaker of today, Sebastiano Argenti from the University of Basilicata, Italy. He's going to talk on gradings on simple leaf superalgebras. Yeah, please.
Okay, thank you. So first of all, I want to thank the organizers for inviting me to give this talk. Yes, today I want to talk about simple superalgebras and their gradings. In particular, I will show some of the latest results, which are based on a joint work with Mikhail Kochetov and Felipe Yasumura. Um, it is some of these topics is a rather technical result. So for the most part, I will skip on the fine details, but I just want to give you an overview of the topic um, and also discuss the possible strategies that you can use to tackle the problem, what are the main difficulties and their solutions. So let's begin. Okay. So, first of all, what is a grading? So, fix a vector space V. A grading gamma is just a family of subspaces such that this vector space is decomposed in the direct sum of these subspaces, which are called homogeneous subspaces. And in general, we assume that these homogeneous components are indexed by some set S generic. What is a set grading on an algebra A? It is the same thing as a grading on A as a vector space, but with an additional axiom. We assume that for any pair of elements of S, say S1 and S2, the product of the elements in the respective homogeneous spaces must lie in another homogeneous space. So there exists some T in S such that the product is in A with T. And since the sum is direct, this T is necessarily unique if the product is not zero. This is a set grading. Then we are interested in G grading, where G is a group. The definition is similar. It is a set grading on A, where the indexing set is the group G, and we require that the product of homogeneous elements lies exactly in the homogeneous subspace with the degree, the product of the degrees. We say that gamma is a group grading, so in principle it's an arbitrary set grading. We say it is a group grading if it can be realized as a G grading. So there exists some group G such that the homogeneous components are precisely the same. So we have also an injective map from the indexing set, which is also called the support, to the elements of G. To each grading, we can associate a group, the universal grading group, and it is formally defined in the following way. It is the group generated by the support, and we assume the relations that the product of two elements must be the element in which the product of homogeneous elements lie following the axiom. So as you can see in the formula, S1 times S2 equals T if and only if the homogeneous elements of degree S1 and S2 lie in the homogeneous space of degree T. But we have to assume that only we impose this relation only if and only if the product of the subspaces is not zero. This is because we want that the element T is uniquely determined. It is called the universal grading because it satisfies an universal property. whenever we have a realization of gamma as a G grading, so an injective map from the support of gamma to the support of G, such that the homogeneous space coincide, then this injective map can be extended to an homomorphism from the universal group of gamma to G. Uh, Therefore, the universal group, in some sense, it can be used to describe all realization of a grading. A similar notion is that of abelian universal group. It is just the abelianization of the universal group, and it satisfies the analogous universal property, but now we consider only gradings over abelian groups G. Okay, for our purposes, we will consider only abelian gradings, since we will deal with Lie superalgebras, and one can prove that on such algebras, every grading is equivalent to an abelian, any group grading is equivalent to an abelian group grading. Pay attention, there could be also gradings that non-group gradings, so gradings that cannot be realized as a group gradings. But whenever we have a group grading, then in case of Lie algebras, it can be realized as an abelian group grading. We want also to compare different gradings. Okay. To compare different gradings, we can introduce a notion of isomorphisms. So take A and B graded algebras, which just means they are algebras with a grading. These definitions, they could be algebras in general, not necessarily algebras. They could be also associative algebras, non-associative algebras, etc. This is a very general definition. Okay, we say that A and B are isomorphic as graded algebras if and only if they are isomorphic as ungraded algebras, and more, the isomorphisms preserve the grading. So elements of degree G are sent to the map, the isomorphisms phi, to elements of B of degree G. There is a weaker notion that is of equivalence that can be used to compare gradings on with support on different groups. Not that for the notion of isomorphism, we require that both A and B are graded over the group G, the same group. For the notion of equivalence, we do not require that they are graded on the same group. Also, the notion of equivalence can be defined for set gradings in general. Okay, what does it mean that they are equivalent? If there exists a map alpha between the supports, the subsuport of the gradings, recall that the support is just the elements for which of the set S, for which the corresponding homogeneous space is not zero. If we have such a map and there is an isomorphism from A to B that sends homogeneous elements of degree S in homogeneous elements of degree alpha with S, we say that A and B are equivalent. Okay, there is okay, this is important because such a map alpha always extends to group isomorphism, to a group isomorphism between the universal grading groups. So also this case can be dealt with group homomorphisms or isomorphisms. Okay, let's talk about refinement coarsening, which is another way of comparing gradings. Now we fix an algebra A, so we compare gradings on the same algebra A. We fix two gradings, gamma and gamma prime. We say that gamma is the refinement of gamma prime, or equivalently, that gamma prime is a coarsening of gamma, if for any element of the support of gamma, there exists an element of the support of gamma prime, such that the homogeneous elements of degree S in the first grading are also homogeneous of degree T in the second grading. Okay, this is the abstract definition. Concretely, this means that with the grading gamma prime, the homogeneous components of the grading gamma prime can be further decomposed in smaller components, and this gives the first grading gamma. We say that a grading gamma is fine if it admits no proper refinement, so we cannot decompose further. And not that any finite dimensional algebra, if A is a finite dimensional algebra, every grading is a coarsening of a fine grading. This is because we start from any grading, we can uh, decompose further the homogeneous components. Since A is finite dimensional, there will be a point when we cannot decompose them, since the dimensions of the homogeneous components is always strictly less. So fine gradings can be used to describe all the gradings in some sense. And also this can be described in terms of the universal group. In fact, a G grading is a coarsening of the grading gamma if and only if there exists a group homomorphism between the universal group of gamma and G, such that the grading over G is the so-called induced gradings that is defined as in the slide. So you take as the elements of degree G, you take the linear span of all the elements in the preimage of degrees in the preimage of G. Okay, so we are interested in classification, on the classification of gradings in some algebra. So we know how to compare different gradings. We want to know how many of them there exist and if they are equivalent or not. We can perform this classification in two different ways. At least these different ways are considered in literature. We can classify fine gradings up to equivalence and also G gradings up to isomorphisms. Okay, in some sense, we can go from one classification to the other. Assume we know all fine gradings up to equivalence. We said any G gradings is a coarsening of fine grading. So, in principle, I could, starting from the list of fine gradings, I could compute all the coarsenings and so obtain all their gradings, the G gradings. The problem is that this list in practice will have some repetitions, and if the algebra is large, it's not trivial to determine which of the G gradings obtained in this way are isomorphic. So often, it's not trivial to go from fine gradings to G gradings. On the converse, if we know all G gradings for all possible group G, of course, by determining which of these are fine, we can obtain the first classification. Again, if the algebra is very large, often this is not practical. In literature, for many algebras, in small algebras, this has been done, but in general, this is a difficult task. So these two cases have to be treated separately. Okay, let's make. Okay. For example, take the algebra 2 by 2 matrices. Okay, there are some important gradings. The first one is so-called Cartan grading, which has a universal group Z. One homogeneous component is the one with diagonal matrices. Another homogeneous component of degree 1 is matrices with the only non-zero element in the in the upper position, okay, non-diagonal position, and also the last component when there is just one non-zero element. There are also other gradings, for example, the Pauli grading, which has universal group, the Klein for group, which is isomorphic to Z2 squared. Okay, grading is in the slide. These two gradings are both fine. They cannot be decomposed further. In the second case, it's clear. Every homogeneous component has dimension 1, so clearly it cannot be decomposed, but you can prove that also the first grading, where the first component has degree 0 has dimension 2, but also it cannot be decomposed. And so it cannot be refined, we will say. There are other gradings. For example, the superalgebra grading, so-called because M2 is a superalgebra with this grading, associative, uh, where it is just decomposed in two subspaces, the one of diagonal matrices and the one of off-diagonal matrices. This grading is not fine. You can obtain it as a coarsening of the previous two gradings. As you can see, it is a coarsening of both the Cartan grading and the Pauli grading. So even this is a small example, a small algebra, you can see that fine gradings and G gradings are different, must be classified differently. Okay, I did not specify M2 as an algebra with respect to which operation. Okay, this grading work if you regard M2 as an associative algebra, but so the usual matrix product. But it also works if you consider M2 as a Lie algebra with the Lie bracket, or even as a Jordan algebra. And this is a very important example because it is the main building block of many of the other examples that we will consider. Okay, in general, the history of classification of gradings on simple algebra is very long. For example, on associative algebras, it was done by Bakhturin, Segal, Zaitsev. But it's also done, for example, for Lie algebras, simple Lie algebras. You can see for Bakhturin, Koshitov from some infinite series of simple Lie algebras. The first is one, Daniel Duque did the classification of fine gradings. Okay, the first one was of G gradings. Also, I want tell you about the monograph by El Duque and Kochetov, which it is a summary of its most updated reference for this kind of classifications. So it contains both the associative case and the Lie case. And the Lie case is almost completed. Gradings on simple algebras are computed, are classified for any infinite series of simple algebras, except a couple of exceptional algebras, but it is almost done. There is some archive preprint that deals with the remaining cases. So for associative and Lie algebras, the classification is complete substantially. Okay, these were the most pertinent example to my talk, but of course this classification has been done for a great variety of algebras, journal algebras, also for non-simple algebras. I want to focus on simple Lie superalgebras. Okay, so let's give a definition. What is a Lie superalgebras? This was just to give an overview of the vastity of the topic. A Lie superalgebra is a vector space endowed with a binary operation, a bracket, and a Z2 grading. Z2 grading is a vector space, which just means that the bracket of homogeneous elements is also homogeneous, and the bracket of elements with same degree is even of degree 0. The bracket of elements with different degree is odd, or of degree 1. Then we assume as axioms the superversions of antisymmetry and the Jacobi identity. So they are the analogs for the algebras, but there is a twist with the sign. which depends on the degree of the elements that you consider. Okay, this is the straightforward definition. There is also an equivalent definition that is very useful in the application when you do computations. So take a vector space with a decomposition L0, L1. It is equivalent to define the Lie superalgebra in the following way. You assume that L0 is a Lie algebra, because going back, if you take only elements of degree 0 in these axioms, you reduce precisely to the axioms of Lie algebra. So L0 is a Lie algebra. L1 is a L0 module. Then there exists a symmetric bilinear L0 invariant map that takes as an argument two elements of degree 1 and produces an element of degree 0. And you also impose this further axiom that if you take the bracket with the same element repeated 3 times, you obtain 0. Okay, just a quick remark on the field, on the base field. All I want to say today will be on assuming a base field algebraically closed and of characteristic 0. Many of these discussion can be extended, some parts not. For example, this definition is equivalent only in characteristic different from 2 and from 3. But for now on, assume that we work in characteristic 0 and also that the field is algebraically closed. Okay, let's talk about the classification of simple Lie superalgebras. This is a very famous theorem by Victor Katz. So, any simple finite-dimensional Lie superalgebra over, again, an algebraically closed field of characteristic 0 is isomorphic to either one of the simple Lie algebras, which you know there are some infinite series and some sporadic examples, and it is analog. They can also be simple Lie superalgebras. And again, we have some infinite series and some exceptional examples. Okay, so we have the classical Lie superalgebras, which are the Lie superalgebras of which L1, which is always an L0 module, we also assume that it is semi-simple. Then it is a classical Lie superalgebras, and then we have the infinite series of basic Lie superalgebras, which are the analogs of more or less of the corresponding Lie algebras. Then we have two infinite series of strange Lie superalgebras, some exceptional case. The first two are just two exceptional cases. The third one is again an infinite family, which is just a deformation of the algebra D21 with some parameter alpha. More on this later. And then we also the Cartan type Lie superalgebras when L1 is not the semi-symbol, and there are 4 infinite families. Okay, so we want to classify the gradings on all of these algebras. As I said before, this is still an ongoing work. Several people is working on this. It is not completed yet, but a lot of progress has been made. I will focus later on the exceptional superalgebras. So okay, just to be clear, what is a grading on a Lie superalgebra? Is a decomposition using in homogeneous spaces. We need that the bracket satisfies the grading property, and we also require that the homogeneous component in the Z2 gradings are compatible with the G grading. So both L0 and L1 decompose further within the G grading. Not that a G grading on the superalgebra can be refined, can always refine to a Z2 times G grading. So this means that if gamma is fine, the support of the even and odd part must be disjoint. And also this also determines the so-called parity homomorphism from the universal group to Z2. Okay, gradings on an exceptional symbol in superalgebra were considered by many authors. So, for example, this is first paper in 2017 from Bakhturin, Denadai, Hornat, Dos Santos, and Kochetov. So they tackled the first series, QQN, also in case of Jordan superalgebras. Then other infinite series later. And then one most recent work is of the PhD thesis of Denadai Hornat, and that it deals with almost every infinite series of Lie superalgebras. So it includes all the previous works and some other things that now I will explain. And also, recently there was a new paper on arXiv that so where you can find this information other than on the PhD thesis. Okay, what are the techniques used to classify gradings? The first one is the duality between gradings and actions. So assume that F is algebraic closed of characteristic 0. If A is a finite-dimensional algebra, the automorphism group is an algebraic group. Also, if G is finitely generated, abelian group, the dual is an algebraic group, which is just the group of characters, so homomorphisms from G to the base field F. So, using this, if we have a G grading on A, then we can define an action by G hat, by the dual, in the following way, acting on homogeneous elements. On the converse, if we have an action of G hat, since G hat is a quasi-torus, which just means it is the direct product of the multiplicative group of the base field several times, and of a finite group. We have all its representation are diagonalizable, and so we obtain that the eigenspan decomposition is precisely the grading. So this is a bijective correspondence. What is the main consequence? That the classification of gradings depends only on the automorphism group of the algebra. So take two algebras, A and L, possibly with different signatures, which means that to divorce totally different operations, maybe some as a binary operation, other are ternary operations. First algebra maybe is associative, the second algebra is the algebra. Okay, they could be any kind of algebra, but with isomorphic automorphism group, then there is a bijective corresponding between gradings on A and gradings on L. So for example, we know the gradings on all associative simple algebras. This technique is called transfer of gradings. It was used in that work I was citing before to obtain for each simple Lie algebra, superalgebra in the series. They found another algebra with the same automorphisms group, and so for which the classification of gradings was already known. In this way, they were able to transfer the classification of gradings from one case to the case of Lie superalgebras. This works for all the series A, B, C, D, P, and Q, except for the algebra, the first algebra of the series A, because it is an exceptionally large automorphisms group. So our work stems from this problem. How can we describe, what other technique can we use to describe the gradings on A11? And then it turns out that we can relate this algebra to the exceptional symbol superalgebras. So we need to introduce some more notation for another technique. So fix a grading, we define these groups, subgroups of the automorphisms group. The diagonal automorphisms are that act as a multiplication by scalar on the homogeneous components. The stabilizer is the automorphisms that fix the homogeneous components, and the automorphisms of gamma, automorphisms group of gamma is of maps that permute the homogeneous components. Okay, not that in the previous definitions, stabilizer is the automorphisms group of the Gradings, while out gamma is the group of self-equivalencies. Okay, this conflict of notations. Okay, this is a technical remark on some hypotheses, finite hypothesis. Uh, uh, in fine group gradings, the stabilizer coincides with the diagonal group. And this is useful to describe fine gradings. Gamma is a fine grading if and only if the diagonal group is a maximal quasi-torus in out A. So we have a bijection between the equivalence classes of fine abelian group gradings and the conjugacy classes of maximal quasi-tori in the automorphisms group. So we can use the automorphisms group to compute all the fine gradings. Then Elduca and Kocherov introduced another notion of almost fine grading when the connected component of the identity of the diagonal group is a maximal torus in the stabilizer. So under some assumptions, they proved a characterization of almost fine gradings. So in terms of the universal grading group, so if delta is a fine grading, delta prime is a coarsening, so it is obtained by the quotient with a subgroup of the universal group, then delta prime is almost fine if and only if the kernel of the quotient is a subgroup of the torsion group of U, and also there is another condition about the derivation of A. Okay, besides the technicalities, the main point is that this theorem allows from a fine gradings to obtain all its almost fine coarsenings because we just need to determine in all possible ways the group E. But these two conditions are very restrictive, so it turns out that it is easy to do this computation. Okay, then if we have an almost fine grading, consider the natural map, the natural projection obtained by the quotient with the torsion part. Alpha from U to G is admissible if the restriction of the homomorphism obtained by the direct product of alpha and this natural projection is injective when restricted to the support. Okay. We care about this admissible homomorphism because of the following. Define the well group as the automorphism group quotient the stabilizer. We can identify W of gamma with a permutation of the support, so it extends to a subgroup of automorphisms of the universal group. Then we can obtain a classification theorem of any G grading. This is a theorem proved by Elduca and Kocherov. It is an archive preprint. But if we have a set of representatives of equivalence classes of all almost fine gradings, and as I said before, it is easy to have it once you have all just the fine gradings, then any G grading is obtained as a coarsening of gamma through an admissible homomorphism, and two such coarsenings are isomorphic in the if and only if the admissible homomorphisms lie in the same orbit of the Weyl group. Okay, what is the main point of this theorem? If I have a classification of all fine gradings up to equivalence, I can obtain the classification of all G gradings up to isomorphism if I compute the Weyl groups and the admissible maps. Okay, this is a groundbreaking work because in my introduction I said that the two kinds of classification are different. It's difficult to go from one to the other. Thanks to this work, in fact, it is possible to go from the classification of fine gradings to the classification of G gradings. This is the technique that we used. So take the automorphism group and compute all the fine gradings. The automorphism group of the exceptional symbol superalgebras was computed by Serganova in 1985. Also, all symbol superalgebras we use, but we focus on the exceptional ones. This classification, this computation was used by Draper, Duque, and Martin Gonzalez to obtain all fine gradings up to on the exceptional symbol superalgebras. So use their theorem to compute the almost fine proper corsings, their well groups, and their admissible homomorphisms. And so we obtain the classifications on the exceptional simple superalgebras. Okay, this is the general strategy. I will give the details in the first case and then just say a few more things for general one. Okay, take G3, the firstly symbol superalgebra. L0 is the direct product of SL2 and Z2, where SL2 is the 2 by 2 traceless matrices, the algebra. C and C is the Cayley algebra of the split of octonions. G2 is the algebra with its derivations. V is the natural module of SL2. So they are matrices that act on columns of 8 2. And C0 is the again the natural module of G2. Okay, you define G3 in this way. How we can define several gradings on C. Okay, maybe let me skip this part. The main point is that we have two types of gradings. The Cartan type gradings obtained in some way. You take three elements of G and assign degrees in some way. Also, we have the Pauli gradings obtained from the Kelly-Dixon doubling process. I recall the classical process on R. From R, you obtain C, then the quaternions, and then the octonions. If you do this on an algebraically closed field F, and each step you add the grading to the other elements, adding a generator of order 2 of the group, of the grading group. Okay, you obtain that F has the trivial grading. Then second step, you have a Z2 grading, then M2F as a Z square grading, which is the poly grading. Oh, this is why it's called poly grading. And the last step, the octonions or split of octonions since the field is algebraically closed, you obtain a Z2 cube grading. And so if you have a subgroup for G isomorphic to that Z2 cubed, you obtain a grading over G. So how can you construct a grading? You fix an element of G, decompose the natural representation of SL2 in two subspaces of degree G and G-1. Consider a grading on C of either type. The grading on V induces a grading on SL2. The grading on C induces a grading on C0 and G2. So you patch together all these gradings on the algebra G3, which is thus obtained by these four ingredients. And you obtain several gradings. Okay, among them, the theorem I was setting before, you obtain, in this way, you can classify all the fine gradings. And this was done forever, just up to equivalence, just two fine gradings, one of Cartan type, one of poly type. And using this theorem, we were able to classify all G gradings. I will skip the full classification theorem. I will just describe you how we can describe the list of gradings in a compact way using this table. We found that all G gradings are in two families. Each why two families? Because we have two fine gradings up to equivalence. Okay, we proved that they are also almost fine, and so their coarsening give respectively the two families of gradings. each family is defined by some combinatorial data. For example, on the Cartan grading, you fix three elements of G for the K-algebras and another elements of G for the natural SL2 module. So in the table, in the first column, we have the family. In the other two columns, we have the combinatorial data. Then we have that gradings from different families are not isomorphic. Gradings in the same family are isomorphic if and only if their parameters are equivalent in some sense. And in the last column we describe the equivalencies. For example, for the Cartan type gradings, we can invert G. So instead of G, we will take G to the -1 and also simultaneously invert all the elements H1, H2, H3. So this is just a compact way to describe the list. Okay, the other exceptionally superalgebra is the algebra 4. We deal with this case in a similar way. So it is L0 is the sum of SL2 and SO7, where SL2 is the same as before. SO7 is orthogonal algebra of 7 by 7 matrices. L1 is again the tensor product of two representation. V is the natural one, W is the spin representation. And again, we have defined gradings, and there are 5 of them. I will skip the details. But in a very similar way, doing all the computation with the same strategy, we obtained an analogous table. So as you can see, we obtained the result. Okay, finally, the last exceptional case, which is a family of deformations. Okay, define the algebra in the following way. Take L0 as 3 copies of SL2, the direct sum of 3 copies. Then on L1, you take the tensor product of the respective natural modules. You can prove that there's a unique symmetrical zero invariant bilinear map from L1 times L1 to one of these components. So every symmetrical zero invariant bilinear map is a linear combination of these three. And so, as we said before, a Lie superalgebra is just a Lie algebra with a module and symmetrical zero invariant bilinear map, and then another axiom. The fourth axiom gives that the three coefficients of the linear combination must sum to 0. Okay, so take these elements. This is simple if and only if all of them are not 0. Moreover, they are, in fact, we can scale all the coefficients and we obtain isomorphic algebras, and we can permute them. So, okay, therefore we can identify the space of the parameters with the projective line. So they are parameterized, with alpha, and this gives the infinite family T1 alpha. So we see as how S3 acts on the projective line. We can obtain different families of these superalgebras. They are separated by the automorphisms group. Serganova proved this theorem. Their inner automorphism group are all the same. Their outer automorphism group is isomorphic to the stabilizer of alpha, the element of the projective line, under the action of S3. So we obtain several cases. You have an orbit with 2 elements, where omega squared, where omega is a primitive cubic of unity. Then 2 orbits of size 3, and then all the other elements lie in a generic orbit. Since the gradings depend on the automorphism group and these different kinds of orbits have different automorphism group, we have different classifications. So the first case, in a generic orbit, we have just 3 families. And again, they depend on the grading on SL2, so they are of Cartan type, polytype, or mixed type. So they are different in this sense. A similar argument applies to the omega, and one more family appears. It is related to the outer automorphism. And then again, we also do this on the last family of the symbol superalgebras in this series, which is isomorphic to an orthosymplectic superalgebra. The gradings were already known. Yeah. Luckily, the classification we obtained is the same of the classification that was obtained by the other authors. So we are pretty confident that our result should be correct. Then the last case, the last orbit, we have an algebra which is not simple. It has a unique ideal. This ideal is precisely isomorphic to PSL22, which is the algebra A11, the only algebra in the classical series for which the classification is not known. So we could relate the automorphisms of D1 to those of A11, and what happens is that the two automorphisms group are isomorphic. So we can use the transfer technique, starting from an exceptional algebra. Okay, we need to twist the technique since the automorphisms of D1 and of D minus 1 are different, are not isomorphic, more precisely, but we were able to prove using central extensions and other machinery an analog of the transfer theorem. So the classifications are in bijective correspondence. In turn, this gives a classification on N11. Okay, so using this transfer technique in 3 steps, we were able to obtain the classification also for this symbol superalgebra A11. And as you see, we have the same number of families as of the orthosymplectic algebra, as you can expect since we use the transfer technique. But in some sense, they are still have some differences, as you, for example, the equivalence is defined in a different way, since this is a nice fact that we can transfer the grading, but these grading are not isomorphic. So neither the universal groups are isomorphic. So they're very similar classifications, but they are fundamentally different. Okay, so this is the story I wanted to tell you today. This is the full references list. I already mentioned many of these papers in my presentations. And so thank you for your attention.
Thank you very much for your talk. Other questions? Okay, thanks again for your nice presentation. And I also thank all the participants for being able to come here today. So have a nice week. See you next Monday.
Okay. Thank you. Good evening.